Welcome to the deep dive. Today we're really tearing into the new frontier of measuring machine intelligence, the ARC Prize V3. This benchmark, it's designed by Francois Chollet and his team, and it's trying to define what true generalized learning looks like,
Yeah,
in an AI system.
exactly. And our sources today are straight from a fireside chat with the creators, so pretty direct insights into their thinking.
Yeah, it's going to be good. Because V3, it isn't just another update, right? It sounds like a rethink of the challenge.
It really is. So our mission basically is to figure out what new abilities V3 is actually testing for,
Right.
how they're defining intelligence in practice, and this big point they make, why solving V3 is not the same as getting to AGI.
Yeah, that disclaimer seems important. And we kind of to kick off with this term they're using, micro-AGI.
Micro-AGI.
Because, you hear AGI, you think huge, complex stuff, like world-changing AI.
Right, Skynet or something massive.
Exactly. But the source material, it really emphasizes that this challenge is tiny. It's focused completely on how efficiently the system can, pick up new skills.
And discover the rules in these small new environments.
Okay, so efficiency is the key word there.
That's the core idea, yeah. It's about the properties of general intelligence, not just making the task bigger and bigger.
But before we dig into those properties,
Yeah.
that boundary condition you mentioned.
Yes. Crucial. They are very clear. Solving V3 is not enough to say you've built AGI. No way.
Okay.
If you solve it, you've definitely cracked something important about learning efficiency. A big piece. But it's not the whole picture. Not general intelligence across the board.
Got it. So necessary but not sufficient, maybe. Okay, let's unpack the new capabilities then, because this sounds like a big jump from V1 and V2.
It is. V1 and V2, they relied a lot on what the model already knew, kind of.
Yeah.
V3 forces the AI to demonstrate three core abilities that feel much more human.
Okay, what's the first one?
First, the system has to discover and acquire its own goals, just from experience.
Hang on, its own goals, not like complete this task I'm giving you.
Exactly. It's not find the blue square. It's more like the system tries stuff, it gets some kind of reward signal when the square turns blue, and it has to figure out, oh, okay, making the square blue must be the goal here.
Wow, okay.
Yeah.
That's fundamentally different. It's not just solving problems, it's like defining the problem in the first place.
You got it. That's number one. Number two is the need for temporal planning.
Temporal planning. So thinking ahead.
Yeah, thinking ahead. Moving beyond just reacting to the immediate situation. The agent needs to form multi-step plans over time. Think maybe 10, 20 steps ahead to achieve whatever goal it just discovered.
So being strategic, not just reacting step by step.
Precisely. And the third one, maybe the biggest shift, is the move to interactive learning.
Interactive learning.
Meaning the agent has to collect its own data by actually doing things in the environment, interacting.
So it can't just be fed a giant data set, like here's a billion examples, now learn.
Nope. No passive learning from static data. It has to experiment, poke the world, see what happens, learn that way.
And that interaction, that's tied back to the efficiency thing you mentioned. What's the actual target? What makes it micro-AGI?
The target metric is pretty demanding. Systems have to hit human-level information efficiency and human-level action efficiency.
Human level. Break that down. What does that mean?
It's not about how fast the computer runs. It's about generalization. How much new skill, how much useful knowledge do you gain for each bit of information you see or for each action you take?
I see. The learning rate, essentially.
Exactly. That ratio, the skill gain per unit of experience, has to match what a human can do when faced with something totally new.
Okay, so why make the environment so small then? Why micro? If the goal is human level efficiency, why not a complex 3D world?
Well, that's the clever part, I think, the microscale.
Yeah.
The games are simple 2D grids, visually simple, low data complexity, you could say.
Right.
And you learn them fast. A few minutes, maybe. Any human could probably figure them out pretty quickly.
So the complexity isn't the point.
Not at all. The point is to isolate that generalization mechanism. If an AI can learn super efficiently in these tiny, novel settings, well, the thinking is it must have the right kind of cognitive architecture.
An architecture that could, in theory, scale up.
Exactly. If you solve V3 the right way efficiently, without just brute forcing it or finding some weird shortcut, then you've likely got the core learning engine, the ingredients needed for scaling towards broader AGI.
So it's the how of learning they're grading, not just if you solve the puzzle.
You've nailed it. Measuring the right ingredients for future scaling.
Okay, that logically brings us to the elephant in the AI room right now, large language models. LLMs.
The big question.
They're everywhere. They're incredibly powerful. Are LLMs, are they enough? Are they the right foundation for the kind of intelligence V3 needs?
The creator's answer. It's a very clear no.
Wow. Okay. A hard no.
A hard no. LLMs alone are definitely not sufficient for the kind of efficient, continual learning V3 demands.
That's a really strong stance given everything LLMs can do. What's the fundamental problem? Is it reasoning?
It's not primarily about reasoning power, though that's part of the picture. The core issue is efficiency, radically different efficiency.
Okay.
Think about how an LLM learns. It's like this giant repository of knowledge, right? Patterns extracted from massive data sets using gradient descent.
Billions, trillions of data points.
Exactly. And gradient descent, well, it needs tons of examples to nudge the weights just right, to get a skill to generalize properly.
Whereas humans
can often generalize from just one or two examples, sometimes instantly. The V3 creators estimate that gradient descent, the engine behind LLMs, is something like 4 to 5 orders of magnitude less efficient at skill acquisition than human intelligence.
Wait, 4 to 5 orders of magnitude? That's huge.
Yeah.
That's like 10,000 to 100,000 times less efficient.
Yeah. So put it this way. If you, a human, need maybe an hour to really get the hang of a new V3 game principle, a pure LLM-based system using current methods might need the equivalent of 10,000, maybe 100,000 hours of similar experience to achieve the same level of generalization. The efficiency gap is just enormous.
Okay, that frames it very differently.
Yeah.
It's not about can it learn, but how much data does it need to learn?
Precisely. Think of an LLM as a giant library. Adding a new core concept efficiently, it's like having to restructure the whole building and rewrite millions of index cards.
Whereas a human just files it away.
Kind of, yeah. Much more targeted update. According to the V3 philosophy, AGI's defining trait is that efficient filing mechanism. LLMs could be the memory, the knowledge base maybe.
But not the core learning engine itself.
Exactly. The efficient interactive skill extractor is the missing piece they're trying to benchmark.
Okay, so it's not the compute bottleneck we usually talk about, it's an efficiency bottleneck. Now, what about the visual aspect? I remember people looking at ARC, V1 and V2, seeing the grids and saying, it's a vision problem, we need better VLMs.
Right, that was a common take.
Is V3 still fundamentally about visual perception?
Nope. Absolutely not. They are very explicit. V3 is a reasoning benchmark, not a vision challenge.
Even though it looks visual, with the grids and colors.
Yeah. The key is that the game state, the grid, it's already provided in a format computers understand easily. It's basically tokenized already. You could represent it as a sequence of symbols without losing any information needed for the logic.
So you don't need an AI that can, interpret pixels from a screen capture?
Correct. In fact, they found something really interesting with V1 and V2. Models that used complex vision systems, the VLMs, actually did worse.
Worse? Why?
Because adding that layer of real-world visual interpretation added noise and complexity that actually got in the way of the core reasoning task. Pure sequence models trained on, code-like representations of the grids performed better.
Huh. So they deliberately stripped away the perception challenge to isolate the reasoning and generalization.
Exactly. It's a design choice. They're also avoiding things like real-time physics or needing precise timing. It's purely about figuring out the underlying rules and planning.
So if you did want to use a V3 solver for, say, robotics,
you'd basically plug it into a separate perception module.
Yeah.
Something that takes the messy real world and translates it into the clean, symbolic state the V3 solver understands.
Okay, that clarifies a lot. Now,
yeah.
Here's where things get, a bit weird maybe. For a hardcore AGI benchmark, one of their main design goals was optimizing ARC for fun.
Slightly. Yeah, it does sound a bit strange, doesn't it? Fun.
Yeah. For an AI test.
Right. It seems almost frivolous. Why prioritize fun in serious science?
Well, the rationale is actually pretty clever. It's got two parts. First, it's about making the benchmark sticky, making it a cultural thing.
Cultural artifact, yeah, I think they use that term.
Right. If the games are genuinely fun to play, more people will get drawn in. Not just AI researchers, but maybe game designers, creative types, people who wouldn't normally touch a dry benchmark. So it broadens the community, potentially bringing in different kinds of thinking to solve it.
Makes sense. If it's boring, only academics will bother.
Exactly. That's the cultural angle. But there's a scientific reason, too. It's about tapping into human introspection.
Introspection. How does fun help with that?
Well, if a game is fun, you, as a human player, get really engaged. You try harder. you're motivated.
Okay.
And then the researchers can study how you solved it. They can ask you, what was going through your mind? When did you have that aha moment? What pattern did you spot?
So you get better data on the human problem-solving process itself.
Exactly. You leverage human metacognition. If the game is boring or frustrating, people give up or don't think deeply, and the insights you get from them are poor quality. Fun equals high-quality human data.
And they actually have a theory of fun they used, something about the learning rate.
Yeah, they mentioned playtesting like over 100 early game ideas. Their takeaway was that peak fun happens when the environment maximizes the rate at which you are learning.
Maximizes the learning rate. Okay.
Yeah.
Think about it. You need novelty, some challenge. It can't just be repetitive execution, but it also has to be tractable. If it's too hard or confusing, you get stuck.
And your learning rate drops to 0, and it stops being fun.
Precisely. So the sweet spot for fun is when the solution isn't immediately obvious, but it's discoverable. It requires that little leap, that efficient acquisition of a new concept or skill, the aha moment.
That easy for humans, hard for AI tension again. The fun for us is cracking the code efficiently, which is exactly what current AI struggles with.
You got it. And that's why they don't expect solutions based on just massive data augmentation, like playing millions of similar games.
Right, because it's not testing a skill you grind.
It's testing the core ability to figure out something brand new, interactively, with minimal prior exposure. Just like a human can walk up to one of these games having never seen it and, get the hang of it pretty quickly because we generalize efficiently.
Okay, so looking ahead then, the benchmark right now, V3, it's targeting human general intelligence because, well, that's the only example we have proof of.
Right, it's the existence proof.
But what comes next, V4, V5? How do they scale this concept up?
The plan is basically to scale up the right ingredients they're measuring in V3. So a massive increase in scale, but applied strategically.
How so? What gets bigger?
Two main things. First, the scale of novelty in time. Instead of learning a concept over 5 minutes, imagine testing continual learning over decades of game time.
Decades? Wow! How do you even create an environment that stays novel for that long?
Yeah, that's a huge challenge. You'd need environments with essentially endless novelty, not just a fixed set of puzzles. Procedural generation on steroids, maybe?
Okay. What's the other scaling dimension?
Environment complexity and interaction. The environment itself needs to become more alive, more adaptive.
Adaptive. Like it changes based on what the AI does.
Exactly, and potentially including other agents, other AIs, maybe even humans within the environment for real collaboration and competition. The environment becomes a dynamic system, not just a static test.
It sounds like that concept of coevolution they mentioned, where you actually need progress in AGI to build the next benchmark. And then that better benchmark pushes AGI forward again. It's a cycle.
It's a feedback loop, yeah. And the really interesting twist there is, what does that next-gen benchmark look like? An adaptive environment with intelligent agents inside.
It starts to sound like the benchmark itself needs to be intelligent.
Kind of, yeah. They talk about it needing to be an intelligent artifact or a proto-AGI in its own right.
Okay, so let's try and wrap this up for you, the listener. The big takeaway here seems to be that the cutting edge of defining and measuring AGI, according to these ARC creators, is really all about radical efficiency.
Efficiency.
It's less about sheer processing power or super complex simulated physics or even perfect vision. It's more about how incredibly efficiently an agent can learn new skills and generalize, how quickly it gets that aha moment from minimal data.
Yeah, I think that's a fair summary. Intelligence, in this context they're trying to pin down, really boils down to the efficiency of acquiring skills from experience. That's the nut they're trying to crack with V3.
So here's a final thought to chew on. If the ultimate test for AGI, maybe a V5 or V6, requires building an environment that is itself intelligent, adaptive, maybe even containing other agents, essentially the benchmark becomes a sophisticated proto-AGI.
Where are you going with this?
Does that mean the final step in achieving general intelligence might actually be indistinguishable from the final step in measuring it? Is building the ultimate test the same as building the thing itself? Something to think about.